morning, grade 12s. As I had promised, we have a video lesson for today. Some of you will be out tomorrow at the workshop, and this is going to help those that aren't here today because of the workshop. So just a reminder, your assignments were due in today. I won't have them marked for you for tomorrow, but I will have them marked for Monday. And yes, I expect you to come and pick them up. So on Monday, even though there's no regularly scheduled classes, you are supposed to be here. And it's a great opportunity for you. So there is attendance first thing in the morning, and then there's attendance right after lunch in homerooms. So you are also supposed to come and get your math assignment because your test is on Tuesday. So that's just a reminder on that. We're going to take a little bit of a break from logarithms, but we are going to come back to them because part of what we're going to be studying in this unit uses logarithms. That's why you have the two units together. So this is called Sequences and Series, Chapter 6. Hopefully that rings a little bit of a bell with you because you studied sequences and series, one of the first units in grade 10. So a little bit of this will be a refresher and some of it might be new. So first thing I'm going to look at is the different types of formulas. So when we're dealing with sequences and series, this first one is called a recursive formula, and we didn't do a lot of that with our grade 10. But a recursive formula allows us to relate each term to a previous term. In order for this to happen, one or more terms must be given. So we have to have a starting point. Okay? It's based on that number that I know what the next number is going to be. Let's look at an example. And yes, you should be writing down notes. So in example 1, t sub n is equal to t sub n minus 1 plus 1, where t sub 1 is 1. Now, you're thinking, that sounds horrible, right? It's not meant to be spoken, but it's meant for us to understand what does it mean. Okay, so let's look at a couple of things. T sub n, that is our term number, right? So the n's representing the term number, so maybe it's our 6th term, right? So t sub n minus 1 would be the term before it, the previous term. All right, so if this is the term in question, then t sub n minus 1 is the previous term. Okay, so if I want to calculate the 6th term, this is saying find your 5th term and add 1 to it. Okay, well, how do I know the 5th term? Well, the 5th term would say, oh, find the one before it. What term would that be? 4. And add 1 to it. Oh, well, how do I know the 4th term? Well, find the term previous, 3, and add 1 to it. Oh, how do I find the 3rd term? Find the 2nd term and add 1 to it. How do I find the 2nd term? Go to the term previous, which is term number 1. And what's our starting point? 1. And then you add 1 to it. So term number 2 is 2. Add 1, term number 3 is 3. Term number 4 is 4. Term number 5 is 4 plus 1, 5. Term number 6 is 5, add 1, 6. Oh, okay. So you have to go backwards. You need to go to your starting point. And I don't know if just me telling you this has shown you, but there is a problem with a recursive formula. And the recursive formula is that you have to go back to the very start and build everything up to it. So let's look at how am I going to calculate these. So term 1 is 1. Term 2 is the term previous. Okay, that's what this is saying, my previous term. So what's the previous term? Term number 1, and add 1. So term number 1 is 1, Add 1, it's 2. So term number 2 is 2. How do I find term number 3? Term number 3 says you take the previous term and then add 1 to it. So my previous term is 2, and then I add 1 and I get 3. You follow. Term 4 is term 3, add 1. But what is term 3? 3. So this is 3, add 1 to give me 4. And so on. Well, what's some power to recursive formula? Because I don't know about you, but to get to term number 100 looks like a lot of work. And guess what? The only way I can get term 100 is if I know term 99. I can only get term 99 if I know term 98. So I got to have a starting point. So that's important. But you know what? In our culture, what does recursive well are computers. So there is a reason for this. This is something that we would have a loop, a programmable loop. I don't know how many of you do any programming, but it could be a do while loop, a for an X loop, something along that line. Okay? So it's when I say a loop, it's going over and over and over and over again. So it's doing that same process over and over and over again. And that's what this is. So with computers, recursive procedures are really easy. Okay, now let's look at another example. All right, so here, remember we've given our starting term is term number 1, and we're saying term number 1 is 2. So anytime I recall term number 1, I'm going to put in a 2. And so this example says, well, in order for me to find my nth term, I need 2 times the previous term and then subtract 3. Remember that this symbol, t to the n minus 1, is my previous term. Okay, so let's start. Let's find some. All right, so term number 1 is 2. That's my given, my starting point. Term number 2 is 2 times my previous term, which is term 1, subtract 3. Okay, so that tells me that's 2 times 2, subtract 3, 1. All right, so term number 2 is 1. Term number 3, 2 times my previous term. My previous term, term 2 now. Subtract 3. So this is 2 times 1, subtract 3, negative 1. So term number 3 is negative 1. To find term 4, it's 2 times the previous, subtract 3. 2 times negative 1, that's the previous term, subtract 3, negative 5, and so on. And that is what we mean by using a recursive formula. Okay. The next thing we're going to look at has to do with a man, Leonardo of Pisa, right? So we're looking at 1202, around that time. I don't know if that's his birth date, his death date, or just some random date. But we don't know him as Leonardo of Pisa. We know him as Fibonacci 1, 1, 2, 3, 5, 8. Fibonacci, the sequence did create. Okay, and 13 and so on. Well, there's a recursive formula for this sequence. Okay, I don't know if you know this pattern, but let's do this. I'm going to start you with knowing term number 1 is 1. And I'm going to tell you that term number 2 is 1. Let me just take a minute and see if you can write a recursive formula. So that tells me, okay, what would term number 3 be? But you're going to have to tell me that in terms of term number 1 and term number 2. All right. It's not the easiest. But if you know the sequence, it is. 1, 1, 2, 3, 5, 8. Fibonacci, this sequence did create. You know how I love poetry, right? Well, the thing has to do with these numbers and pairing these numbers. So 1 and 1 is 2. 1 and 2 is 3. 2 and 3 is 5. 3 and 5 is 8. 5 and 8 is 13. 8 and 13 is 21. And so on, and so on, and so on. So that's the pattern that's there. So how do I get that? Well, how would I get my third term? My third term says take my two previous terms and add them together. Right? 1 and 1. That gives me 2. That's my third term. Okay, now let's make this, well, let's go fourth term then. Fourth term is term number 3, add term number 2. And so on. And so on. Let's get to the generic type. How can I do this for any number? Well, that's when we say the nth term. This is the general form when we go not to a specific example, but in general, how is the Fibonacci sequence created? Well, it's the previous term, so that would be term to the n minus 1, plus the term before n minus 1. That would be term n minus 2. This gives you the Fibonacci sequence, but you need 2 starting points. And what's interesting is that Fibonacci sequence that we know of 1, 1, 2, 3, 5, 8, we also have multiple other types of Fibonacci's. And that is as long as I know 2 starting numbers and then I add them together. So you could have a sequence that says, oh, term number 1 is 4 and term number 2 is, it has to be bigger than 4. Let's say term number 2 is 5. All right, so you have 4, 5, 9, 14, and so on. And this would also constitute another type of Fibonacci. Okay, where I'm taking the 2 previous numbers, adding them together to get to the next number. So just thought you'd find that a little interesting. So that's working with recursion. What's the downfall of recursion? The problem with recursion is you need to know the number previous. So if I am looking for term 100, I need term 99, which means I need term 98, which means I need term 97, which means I need term 96. And you see that that's a lot of work that we have to do. And unless we have a computer, that's just grunt work. So there is another form that makes life easier for us when we're dealing with sequences. And this is called the explicit formula. Now, Mr. Gallant says it's a little naughty. All right, so you get that? Hopefully you got my joke. Anyway, so this is called the explicit formula. In grade 10, we didn't call it that. Okay, what we called it was the general term. And I can't spell here this evening. And I used to say to my grade 10s, you know what? General has an N in it. This is going to have an N in it. This is going to be more powerful for us. Okay, so our formula, here's an example. This is an explicit formula that we have. T sub n is 2n plus 4. So the definition of our explicit formula says it relates each term according to its term number, n. What term am I in the sequence? So instead of having to rely on the previous terms, I just need to know my placement in the sequence, and that will allow me to know what term I am, what value I have. So remember, n is the number in the placement of the sequence. T sub n is the nth term, the term being the value that it has in the sequence, and n is just its place number in the sequence. It's a little confusing, but we need to really draw on that skill that we had in grade 10. Okay, so here I am given an explicit formula to begin with. Once I have that, I want to find what are the next few terms in the sequence. All right, well, let's start with term number 1. Term number 1 says it's 2 times number 1 plus 4, so that's 6. So the first term in this sequence is 6. term number 2. Remember, its placement is 2. So this gives me 8. Term number 3. Its placement is 3rd. So that's 6 plus 4 to give me 10. And so on, and so on. Right? I'm going to have to bring that up. Give me a second. There we go. So, do you want to see the power in this? I want to know, what is term 100? So right now, this goes 6, 8, 10, and so on. What is term 100? I don't need to know what term 99 is to do this. Term 100 is 2 times its place number, so it's placed on 100th position, plus 4. So this gives me 204. So I know that term number 100 has a value of 204. See how powerful the explicit formula is, or what you would know as the general term. It's very powerful for me to just say, I want to know this term of the sequence. All right, I'm going to give you a chance right now to look at something that's a classic computer problem. And it's done by Edouard de Lucas in 1883, called The Towers of Hanoi. And I'm just going to see if, oops, missing my pen. I haven't tried this. Let's see if we can delete. Go to the web page. And I'm just going to pause here until I can get that up. Okay, this gives us a little bit of a background of Towers of Hanoi. It's a puzzle that was invented by the French mathematician Edouard Lucas in 1883. We are given a tower of 8 disks. So in this particular case that we're going to see below, it's going to start with 4, but we can increase that. They're initially stacked in increasing size on one of 3 pegs. The objective is to transfer the entire tower to one of the other pegs, the rightmost one in the applet below, moving only one disk at a time and never a larger one on top of a smaller one. This puzzle is well known to students of computer science since it appears in virtually any introductory text or data structure or algorithms. Its solution touches on 2 important topics: recursive functions and stacks, and recurrence relations. So this is dealing with recursion. And this is a classic example, or a classic problem we deal with. And you will note when we look at our Towers of Hanoi that some of you have played with the Towers of Hanoi that I have in the classroom. So let's see, we have an applet here. Oh no, does this look familiar? Well, no, did you watch Survivor this season? I think it was, yeah, it was the very first challenge that we had with Ozzy and Coach. It was the Towers of Hanoi. Now, what is the idea is that I need to have everything stacked over on this last peg. I can only move one at a time, and I have to put a smaller one on top of a larger one. Oops, just having trouble moving. The thing is, the whole catch is, can you do it in the least number of moves possible? So that took me 15 moves to move 4 disks. Now, I'm curious. Do you think I did it in the least number possible? Frankly, folks, I don't really know. No, I lied. I do know because I'm going to teach you the math, so you do know. But I was just playing with that. I wasn't even thinking as I was doing it. Reset it. I had 15 moves. Let's do this fast. 15 moves. The least number of moves to move these 4 blocks is 15. Okay, hopefully you understand how this process works. All right, so let's just go back to our slide here. We're going to work through this problem. You see it says the number of discs, the number of moves that it would take. So let's reset and let's go down to we have one thing to move. One thing to move, how many moves does it take? Well, except for the fact it doesn't want me to move it. It's too fat for some reason, but let's just do that. How many moves? One. You move it from the left to the right. You can say any idiot can do that. Okay, how many moves does it take to move two? Like it takes one to go here, two to go here, and one more gives me three. So let's start filling in this information. So to move one disc, it takes one move. To move two discs, it takes three moves. How many moves for three discs? 7. 7 moves to move the three discs. We did the 4. Do you remember? It was 15 moves. All right, let's reset. We'll put in 5. There's some beauty to that, isn't there? 31 moves. So to move 5, we've got 31 moves. I'm trying to remember how many are online. I've got 6 discs on my Towers of Hanoi. I just went over to check. How many moves, the least number of moves that it's going to take you to move those 6 discs. That's the whole object of this game. People are saying, oh, it's a play, and they're just playing the game. The object is do it in the least number of moves. So, any guesses? Do you know? 6. Let's see how it goes. 63 moves. All right. Here's the thing. Do you see a pattern? Can you see a pattern between the number of discs and the number of moves? Do you remember how to find patterns when you have a table of values? 1, 3, 7, 15, 31, 63. Those aren't numbers I'm used to seeing. But what are some tricks we have? We can maybe find the difference between numbers. You remember doing that in grade 10? I used to tell my students, well, if you don't see the pattern, the numbers don't like kind of strike you as multiplication or they're not perfect powers, do some work with the y values. Like find the difference between them. Delta y, kind of like a slope. And even see if they're the same. Now we know these aren't the same, but let's look at what happens. Wow. Oh, what's special about these numbers? 2, 4, 8, 16, 32. What do we know about these numbers? They are super twos, right? They're 2 powers. All right, there's a clue to what we're looking at. I don't want to belabor it too much, but there are 2 formulas I'd like for you to work on. Can you find the recursive formula? So that is in terms of the previous term. All right, so I know that if I have 2 discs, all right, that term, number 2, is based on doing something to term number 1. Okay, so can you find a recursive formula? And then there's the explicit formula, the one that's a little naughty. All right, find the explicit formula, and that's the one that's going to deal with what you have written in red. All right, but I'm going to tell you that 2 is playing a very important role. So Mr. Wall will just pause and give you a chance to see if you can come up with your equations. All right, recursive formula. It says let's take my nth term and I have to do something to the term previous to it. And this one is when it's hard. I find some of them hard if I'm just adding or subtracting something, but I gotta do something to it. But, you know, I'm looking at a couple of things. If I multiply by 2, because 1 times 2, right, is 2, and then I got a 3, so I can just add 1. So let's see then, 2 times 3 is 6, add 1 is 7. That's what I'm doing. I am taking and I'm multiplying the previous term by 2, and then I'm adding 1. Don't knock yourself out here if you're having trouble with this, okay? That's all right. They're not always easy to determine. This one's a tough one, right? Because we're dealing with powers. We're going to be dealing with a whole lot easier ones. These ones that we learned in grade 10 were really quite easy, and then the ones that we're going to be looking at for grade 12 as well are going to be easy. This one is a power. Remember we said the explicit formula, can I write a formula that works? And I said, you know, a power isn't like a 2, a 4, an 8, a 16, a 32. Like those are powers of 2. So if I'm looking for my nth term, I'm thinking I've got 2 to some power. But you're saying, but Ms. Kubik, it's not 32. Right? That's just the difference. So let's look back here. In number 1, if I put in a 1, that would be 2 to the 1. And what's 2 to the 1? It's 2. Okay? So if I did that, I have the wrong number, but what's the difference between 2 and a 1? 1. I know, you're thinking that doesn't make sense. Well, let's try another one. Term number 2. 2 to the power of 2 is 4. What do I have to do to get to the 3? I need to subtract 1. Are we on to something? Let's try it with term number 4. 2 to the 4 is 16. Subtract 1, 15. That's our explicit formula. This isn't one that you need to worry about. It is just one that I love. The Towers of Hanoi is a classic problem. And here you can see that there's a recursive formula and an explicit formula for it. And I don't know how much time we're at, but we're not going to worry necessarily about homework. We'll just keep on moving until we get to a point where we can actually do some work. If I get finished and we are able to do some work, fine. If not, we'll be working on that tomorrow. I think you're okay with that. You want to review a little bit about what we had done in grade 10. And in grade 10, we were dealing what was called an arithmetic sequence and series. Series just means I'm adding it up. Oh, adding. That's what arithmetic's about. Arithmetic sequences, or arithmetic, depending on how you pronounce it. Right? Arithmetic sequences deal with adding and subtracting. That's what's called a common difference, right? So I'm going to add or subtract a common difference. I know how much you love general forms of an equation. Yeah, I know it's not your favorite. Let's look at what would happen. Let's take this line by line. Term number 1 is A. How do I get term number 2? This is the recursive part. I would take term number 1 and add a number to it. We're going to call that number D. So we'd have term number 1, which is A plus D. Okay, that's not too difficult. Now, remember, what is term number 2? Term number 2 is A plus D. And what do I do with it with the recursion? I'm going to add the difference onto it. So I get A plus D plus D. All right, again, in recursion, take your previous term and add on a difference. All right, so here for term number 3, I'll have term number 2 plus a difference. What is term number 2? Term number 2 is A plus D plus a D, which gives me A plus 2D. That is term number 3? How do I get term number 4? I'm going to add d on. Right? If term number 3 is a plus 2d, what is term 4? A plus 3d. And so on. What about my nth term? You're saying, okay, well, that's easy. Recursively, it would be my previous term plus the difference. Yep, well, what's the previous term? N minus 1. But it gets complicated, right? So we are going to look at this in the explicit form. How can I simplify this? Well, what do I know I'm going to have? Every one of these, T1, T2, T3, T4, they start with an A. Right? So I know I'm going to have A. Now, what else do I know? What other number I have? Here I have a 3, and here I have 4. Here I have a 2, but there I have a 3. What's the relationship? Well, this ties in kind of with this term number. Subtract 1. Okay, so we're going to say, well, this is n minus 1. And what do I do with it? I multiply it by d. I don't know if you remember the formula from grade 10, but this is the explicit formula for an arithmetic sequence. I need you to know it. You actually have learned it before, so this is just a review. But here's a question. Do you know what those letters represent? We need to know what the formula is, and I've been talking about it. I was going to say tonight, but you're hearing this in the morning. T sub n. The nth term. The term in question that we're looking at. The term is the value. All right, so remember, term gives me the value. That's what I'm looking for. How much does it have for a number? A, the first term in a sequence. Just like the first letter in the alphabet. Makes sense. Well, you can relate it to something like that. What is n? N is the number of terms. For a specific one, or the term number. It is, if I'm in a lineup, it's how many I am into that lineup. Am I the first person in the line, or am I the 10th person in the line? And you're using words like first, second, third, fourth, like a counting number. And D is the common difference. So if I'm adding, it's positive. If I'm subtracting, it's a negative. And that is what we're going to be looking at. Okay. Got your thinking caps on? Right, do a couple of examples. Just a review of what you've done before. Determine the explicit formula for the arithmetic sequence. Explicit formula is saying, I need to have a formula that has n's in it. I just want the general term. I'm not saying, give me the 20th term. Here I just want, in general, what would describe the sequence. Well, here's our formula. Same one since grade 10. What information do we know? Well, we know A is 4. We know D is 5. I'm adding 5 every time. Do you want to know how many terms are in the sequence? No, these ellipses say and so on and so on and so on. Do I know a specific term number? Well, yeah, I know the fifth term's 24, but it has and so on and so on and so on. So I don't know where it ends. So I don't know what value I'm looking for. So that tells me, okay, I need to find the general term. It's this simple, folks. Stick in A, stick in D, and simplify. A is 4. D is what did I do right there? I had to distribute through the bracket, and I get 5n minus 1. You might say, Mrs. Colbert, can it be negative 1 plus 5n? It sure can. It doesn't really matter. Okay. Um, I'm going to leave off with this example that we have. It's a doozy. All right, let's read it. It says, find the explicit formula and the first 3 terms of the sequence that tells me that if term number 12 is 52 and term number 22 is 102. Ooh, I don't know the first term and I don't know the common difference. What do I do? Well, let's say what we do know. We do know that 52 is term number 12. All right? So, how can I write that? Well, term number 12 is equal to 52. That would equal, okay, A plus 12 minus 1 D. Okay? What's 12 minus 1? 11. So I'll just do that. It says this is A plus 11D. Okay, term number 22. That's 102. Well, what is that? That is your first term, because remember, these are part of the same sequence. So they each have the same first term, and they each have the same difference. So this would be 102 minus 1, and do you know what 102 minus 1 is? Sure you do. Right? Even on a bad day, you know that's 101D. All right. Oh. But I don't know A and I don't know D, and I kind of need that in order to find the general term and then to find the first 3 terms. It helps if I know the first term. But let's look at what we have. All right? We have an equation happening here. There's a 52, there's a 102. Let's put these in. We know that this is equal to 52. This is equal to 102. I have a system of linear equations, and I just know how much you love to solve a system of linear equations from your grade 11 course. You can use substitution, or in this case, elimination. And elimination would mean, let's just subtract, change all these signs, add together, and then it's, the thing that I'm having trouble with tonight is, oh, how on earth am I supposed to deal with subtracting? So this gives me negative 90D. Negative 50. Except I must have done something wrong somewheres. Oh, yes, yes, yes. Way back. No one caught it? Yeah, I just caught it myself. Don't you hate when that happens, especially when it's being videotaped? Okay, here's a good thing. Do you see my mistake? All right. What is this? This is N. And what did I do? I put in the actual term number instead. So this, yeah, that's 22. Oops. It's erased. Sorry, folks, and I can't change it. It's just too late. The videotape. Not reteaching the lesson for this mistake. So this comes down to 22D. I knew I just had something wrong there. It wasn't making sense from my answer. So there we go. This gives me a negative 10D equals a negative 50. Sorry about that. Let's just recap. This is my n. That's what should be here. And it is now. So I solve for d, and d is 5. All right, so my difference I'm looking at is 5. How do I get my first term? I stick it back into one of these two formulas. Let's do this. A plus 11 times 5 is equal to 52. A plus 55 equals 52. A is equal to 52 minus 55. A is equal to negative 3. A is negative 3. That's an A, folks. A is negative 3. D is 5. Can I find the first three terms? You betcha. Negative 3. Add 5. Add 5. And so on. So I found the first three terms. Can I now find the explicit formula? The explicit formula would say, okay, well, d sub n is equal to a plus n minus 1d. A, negative 3. D, 5. This gives me negative 3 plus 5n minus 5 for negative 8 plus 5n. Do you need some practice questions? You probably need something to practice. Obviously, I need it to practice. Let's see what we have. Keep in mind that I am aware that it's a crazy week. Page 295, let's just do a couple of each type. Let's try, 2, 4, oh no, what do we want? Even numbers, it looks like I already did. Let's try, oh, I don't like that one. 10 and 12. Page 295, 2, 4, 10, and 12. And I'll be continuing this lesson tomorrow. All right, thank you.